All right, we learned that when faults are trying to move and they can't move, eventually over time they do move, and when they do, the energy that they've stored up is released as seismic waves. So let's talk about what those are today. We're going to be taking notes on the bottom part of this note sheet right here, just in this section. If I go too fast, make sure you stop or back up or do whatever you need to do to make sure you get all the notes and everything filled in. Okay. So seismic waves, this is essentially the release of that energy. I already mentioned that. There's two types of seismic waves. The first one are called primary waves, or P waves. They move the fastest, and they can travel through a solid or a liquid, and they have a compressional motion. So as they move, they're squeezing and stretching as they move along. Primary waves are described as sounding like a car crash or a gunshot when they arrive at an area, but they're very short-lived and they don't usually cause any damage. Secondary waves, these are slower. Obviously, the name second as opposed to primary. They have an up and down motion as they move. And because they have that up and down motion, that obviously causes the surface to go up and down quite a bit and causes a lot of damage as well. So these are your two types of waves, and they can cause the most damage. So how do we measure these waves? We use something called a seismograph to measure these waves. Basically, it's a device that measures how much the ground moves, either up and down or side to side, the measure of those vibrations. And those vibrations are recorded on a seismogram. A seismogram is our readout, our graphical recording. You can see the drum here that is turning as it records that data from a seismograph. And down below, you can see a seismogram, just like the one you have in your notes. The only difference is this one is completely labeled, so you need to label all of yours. A seismogram gives us lots of important information. So you can see right here, this is the arrival of the P wave. That's the first wave to arrive at a seismograph. This is the second one, the S wave. You can see this up and down motion causes much more fluctuation in the needle. And the height of that highest S wave is how we can determine the magnitude, the energy of that earthquake, so how big it is. And then this difference between the P wave and the S wave arrival times, this can be used to tell us how far away the epicenter is from the seismograph that recorded that earthquake. All right, once again, fill out that diagram in your notes. One more thing to talk about here. We know that the P and S waves, they travel at different speeds. This is like running a mile on the track. So you take two students in this room, you say you're going to run a mile. One of them takes 8 minutes to run the mile, and one of them takes 7 minutes to run the mile. So if they run 1 mile, then student B is going to finish 1 minute after student A. If they run 2 miles, then that difference becomes 2 minutes. If they run 3 miles, that difference becomes 3 minutes. And that's how we can tell the distance apart, because we know the rate at which P waves travel and we know the rate at which S waves travel, so that that allows us to measure distance of different earthquakes. So we can look down here in this graph of 3 seismograms I've given you here. You can see the shortest P and S interval is right here. This one's longer, and this one is the longest yet. So we know that this first one is the closest to the earthquake epicenter. This one is the second farthest away, and this is the farthest away based on the difference between the P and the S waves. So that's really cool, how we can figure out the distance to the epicenter. However, if we only have one seismograph, then we only know that it is some distance away in a circle from that seismograph. And if we're going to locate an earthquake epicenter, we actually need 3 seismographs to record the same earthquake, so they could all measure their distance and find out where those circles cross, like the diagram in your notes, like the diagram on the slide here. And where they cross is where the earthquake epicenter is. So that's how we locate earthquake epicenters. Kind of cool. We can get that information out of seismograms. The distance and the magnitude of the earthquake can be determined from a seismogram. All right, today you're going to do a virtual online locating of an earthquake epicenter and measuring of its magnitude. The website is linked for you, and you fill out both sides of that worksheet, read the information on there, and follow along in the steps. Be precise about your measurements. The closer you are, the better off you do. And if you put in a totally wrong number, the website won't let you advance to the next page. So you want to double check some of those and make sure that you understand what you're doing. Good luck.